Hello everyone to this video on the normal law. In fact, there will be two videos to describe and use the normal law because it implies to understand the concept of continuous probability distribution, continuous random variable first. So we have to make some comments and to notice some facts and some elements before describing the normal law, especially this one. First, we can comment something that has been noticed more than 2 centuries ago, especially by Laplace, who was a genius French mathematician. This is the purpose of convergence of some discrete distributions, not all but some of them, and especially distributions that we saw earlier in previous videos that were hypergeometric, binomial, and Poisson distributions. So let's take an example with some figures here, so some values for our parameters. Let's take a population of 5,000 individuals, into which there exist 500 success individuals. These success individuals especially interest us in a certain way, and we have to take 10 people at random inside this population. And of course, it's possible among the 10 people to have some success people. Okay, that belong to the subset of 500 in the population. So this way, if you forbid repetition of one element of one person in this population, you fall into a hypergeometric distribution that can tell you how to calculate the probability of having no one in the success subset among the 10, or only 1 or 2 or 3 or 4 and so on. And you can see that the probabilities decrease extremely rapidly if you want to consider, or if you would have more and more success into your 10 people. So it's due to the fact that there are only 10% success people inside the population. And so your expectation by choosing 10 people is to have only one success over 10. Okay, so it will be the biggest probability here. Probability to have no or 2 people are high themselves. But if you go far from one success, you can see that the probabilities are very, very low. So if you forbid repetition, hypergeometric distribution is the one to be used. If you allow repetition, the binomial distribution will make you calculate the right probabilities. And you can see that both graphs tell you approximately the same thing in terms of values of probabilities. So it's due to the fact that the size of the population, so the uppercase n, is more than 20 times the lowercase n, so that value is 10 here. So 20 times 10 would be 200, and we've got 5,000 people in the population. So this criterion tells us that we can use a binomial distribution to talk about an hypergeometric one. Okay, so both laws are very close to each other. If you want to use a Poisson distribution here, you can see that the calculations lead to probabilities that show us changes compared to hypergeometric or binomial distribution. It's due to the criterions of going to a Poisson law that are not met, in fact. So the probability would have been less than 10%. So here it's 10%. So we are in the limit, at the limit. A second criterion would be that n must be more than 30. And here n is 10. So it's not a good value for applying a Poisson distribution here. So you've got distributions like in the previous videos and like in some examples we treated. So now let's change the value of the lowercase n. Okay, so the size of our sample. And let's take now 50 people in the same population at random. This time, our expectation with a probability of success at 10% at the beginning, our expectation is to have 5 success out of 50 people chosen at random. And that's why on 5, you've got the highest probability. So it's true in a hypergeometric distribution as well as in a binomial distribution. And a Poisson distribution will show 2 equal probabilities. That is a special case because the parameter of the Poisson distribution will be an integer here. So I don't show this because it's not very important for us. So you can see that the distributions begin to really look like each other, even the Poisson distribution compared to binomial and hypergeometric. But let's increase again the size of the sample and go to 200 people to be chosen at random in the population. And now something begins to appear that didn't appear in the first case and in the second one. So of course the 3 distributions are even much closer to each other, but a kind of symmetry appears that wasn't true in the 2 first cases. The symmetry of distribution of probabilities is not here. It begins to be approximately symmetrical here, but not really. And the more the lowercase n increases, so the size of the sample, the more symmetric the distribution of probabilities appear around the expectation. What is our expectation here? 10% of success in the population, so 10% of the sample, that's 20 successes in the sample. 20 is actually indeed in the center of the graph for each distribution, of course. So this symmetry appears. So what did Laplace and some other mathematicians think about that or thought about that? Maybe it would be a unique probability distribution that could describe this kind of case, regardless the repetition or no repetition, regardless the criteria of Poisson or not Poisson, and so on. Maybe a unique law would exist that just waits to be created by someone. But the fact is that it's very complicated to talk about multiple bars, okay? And maybe it would be more relevant to create a curve thanks to a continuous function, a curve that would be and would fit the shape of this bar diagram. Moreover, if you've got multiple possibilities, okay, if your case involves multiple possibilities, maybe the fact to calculate the probability of 24 or 25 success or 14 is not very important in a concrete situation. Maybe the probability to be in some interval is the most important for us, and it will be in most cases. So we begin to think in a continuous way at this kind of thing, and of scheme, of course. Maybe we would be interested in having a curve, and below the curve, in calculating some area that will give us a probability to be in some interval of values of x. So, of course, this law will be named the normal law, and this is exactly something that tends to what we call a normal law that we will discover further, a little bit further in the slides. Now, secondly, what is the context, and to what extent can we talk about a continuous random variable? Here on this graph, we've got discrete random variables. Discrete, that means that we are on the case that the values of x are on a list that is a countable list. You can put numbers on different values of x that can be reached. 10, 11, 12, 13, 14, and so on, and so on, and so on. A continuous random variable doesn't work like that. It works with real numbers, and especially with intervals. So we have to talk about now concrete situations that are not success-failure situations, not based on Bernoulli schemes, but based on something that can be measured in the world, like the size of something or the mass of an object. Okay, that doesn't correspond to a success-failure situation. That's just something that's been measured or that can be measured. So let's have a little activity with the exercise 15 of my document. And let's consider some objects that have been created, handily created. So there are on the red line, here, red row, 200 objects in total, if you add these numbers, 200 objects that have been manufactured. And we are interested in the mass of each object. Of course, we can't measure the mass of something with an infinite precision. So we are only able to tell that the mass is between this and this. Even with a very, very accurate tool. A very accurate tool has not an infinite accuracy. So here in this table, we put the object inside intervals of mass because we don't know with a total accuracy their mass one by one. So we sorted them with respect to these intervals. The frequencies can be related to the percentages of objects. Okay, so here you've got 9 objects between 3.5 and 3.7 kilograms. Okay, and 9 out of 200 represent 4.5%, so a frequency of 0.045, and so on. We would have to graph a histogram of this situation, and in an histogram, the vertical value has to be a concentration. So it has to take into account the width of each interval, so its size. The size of the first, for example, is 0.2. Okay. This number divided by 0.2 will be this concentration. Okay, this number divided by 0.07, this size, equals 1.93, and so on. And now let's display the graph, the histogram of this table. So you can see that the frequencies belong to the interval from 0 to 10, approximately. So I'm choosing a scale here, a vertical scale. And then I'm creating rectangles whose width corresponds to the right interval and whose 8 is the concentration. So here is the graph of every interval of the table here. And you can see that indeed the concentration of objects inside small intervals is very big. Okay, so you've got the distribution of objects with respect to their mass and the real shape of this distribution. Now, in this kind of graph, how could we calculate the probability that an object chosen at random would have a mass between 3.5 and 3.77? This probability would be the sum of the corresponding frequencies, 4.5% and 13.5%. In this scheme, these frequencies represent the areas of both rectangles, the first and the second one. And you can see that you are calculating an area to calculate the probability. So it's a first way to approach the notion of continuous variable and of reading a graph in this context. Now, let's imagine in the same situation that our measures of masses for the 200 objects would have been more precise or more accurate. Here it will be the same. Well, we would have been able to create more intervals, and each interval being with a lower size. So it could look like that as a result on a graph. So here is the distribution of objects with respect to their masses between 3.5 kilograms and 4.1 kilograms. This way, if you want to find out the probability that an object have a mass between 3.5 and 3.7, for example, you would have to add the areas of the corresponding rectangles again. So we're still in a separate kind of values because of the presence of the intervals. But let's imagine now that we can measure the mass of objects that are not 200s but an infinity of objects, and we can measure their masses with an infinite precision. So the blue one was not important, probability to be between 3.7 and 3.9. Now we would have an histogram that consists of an infinite number of rectangles, infinitely thin. So the fact to draw these rectangles is not possible, okay? You just want to know the global shape of your histogram, and it will be described by a curve this time, a continuous curve. And this is really important for us because we just reached the notion of continuous random variable. The mass of something is physically something which is a real number with a possibly infinite number of decimals for each measure. If you want now to calculate the probability that an object in this graph has a mass between 0 and 3.7 kilograms, you have to calculate again an area, but this time it's the area under the curve, between the x-axis and the curve. So it's an integral, mathematically defined. Okay, the probability of x is less than 3.7 is the integral from 0 to 3.7 of the function, which curve is here, okay, f of x point dx. And the probability to be between 3.7 and 3.9 kilograms will be the integral from 3.7 to 3.9 of the same function. So, as you can see, on the vertical axis, I don't talk about concentration anymore. If you go to the limit of continuous variable and of real numbers, the term concentration has been replaced by the term density. But it's the same notion, okay? If you talk about a probability density, it's not a probability that can be read vertically. It's just a density. And a probability in this kind of scheme will be found by calculating an area, okay? Just like before. So, what about the probability of an object weigh exactly 3.7 kilogram? So this way, it would be the integral of the function from 3.7 to 3.7. And of course, it will be 0. So is it true that the probability that an object somewhere in the world weigh 3.7 kilograms is 0? The answer is yes. Exactly no object in the world weighs exactly 3.7 kilograms. It could be possible, but the chance is 1 over infinity, because even in this interval, there are an infinite number of possibilities, and one number taken at random has one chance over infinity to be chosen. The fact is the same for people. For example, no people in the world measures exactly or have a size of 1 meter and 80 centimeters. It's impossible. There will always be a little decimal, okay, more or less 1 meter and 80 centimeters. If we would have the possibility to measure the size of a person with an infinite accuracy, we would find out that this person doesn't exactly have a size of 1 meter and 80 centimeters. Nobody in the world is 30-year-old. It's impossible. Talking about age, it's something that changes all the time, okay? And 30-year-old corresponds to an instant, and the duration of this instant is 0. So the chance to find someone that is 30-year-old is 1 chance over infinity, and so on and so on. So it's not obvious to talk about a continuous random variable, because in every interval that you could consider, even a little interval, there would be an infinite number of possibilities. And an infinite number not countable. Okay, you can number the possibilities one by one and tell, oh, here is one possibility and the following is that. No, if you're talking about real numbers, you can't say or write the following numbers or the number that immediately follows, I don't know, 1.5, for example. What is the following of 1.5? It's impossible to say. It's 1.5, 0, 0, 0, 0, 0, and so on and so on and so on. And at infinity, you can put a 1, but it's impossible, of course. So it's not countable this way. So you have to understand that you only are able to calculate a probability to be in an interval. Okay, this interval or this interval, and never calculate a probability to reach one given value. Okay, so that's exactly the contrary with with discrete random variables that counts successes, for example. You can have 1 success or 2 successes or 3 successes, but not 2.5, of course. And you're interested in given values, and then you can be interested in intervals, of course, by adding probabilities of given values. But this is a completely different type of variable. Then in the next video, we will make them meet in the same kind of exercise, and we will be able to use a probability density to solve a problem that consists in, at the beginning at least, a discrete random variable. So we'll see that later. So now, the continuous random variable can be described like that, and I'm reading with you this time. Let's consider the ideal situation where x can take every possible real value, working in an infinite population. So that was the case I tried to describe you. Here, the frequency's concentration is renamed probability density. So, okay, we already saw that. A probability density of x is a function f, positive and continuous in R, and such that the integral on R, so to negative infinity to positive infinity, the integral, the global integral of f equals 1. So, of course, the probability of every possible value of x must be 100% in the end. So 1. Where a probability is the measure of a surface bounded between its curve and the absciss's axis. Okay, so it looks like that, for example. So I will make a little comment on the next slide. I just choose here symmetric distributions, but of course, in different cases, the distributions are not necessarily symmetrical. Sorry. So you've got a curve of a function, and you can calculate a probability by calculating an area. So here in pink. So what is this uppercase f that appears here? So this uppercase f is named the distribution function of x. Okay, so the sentence just appeared. So f of x is simply the probability of x to be less than the value x, lowercase x. Okay, so you've got here, if we stop at 3.7 on the axis, uppercase f of 3.7, so the probability to be less than 3.7. Here, if we stop at 3.85, you've got in pink the probability to be less than 3.85. This function, so this new one, okay, the last one, is an increasing function of x. Of course, if you stop to the right of one given value, you make the pink area increase. So this f is an increasing function of little x. So that was a quick presentation, okay, here with some graph, but the most important for us will be to describe the normal law, okay. This presentation is a general presentation for every continuous distribution. So let's comment a little this and the fact that I made symmetry appear. So my comment is that the graph for the probability density doesn't necessarily have a symmetry axis, unlike the graphs above could lead us to conclude. The latter is the one of a normal distribution that is actually symmetrical, but you've got continuous variable and continuous distributions that are not symmetrical, like exponential distributions, okay, whose curve are like that, depending on some parameter in the law, okay. You've got p-square distributions, okay, that are not symmetrical again, that are defined, both are defined on R plus, okay, from 0 to plus infinity, okay. So there exist many distributions that are not symmetrical, but our interest in this video is to go to the normal law which curve is symmetrical. So I will make in a few months some videos on other laws, of course, and describe situations that lead to this kind of laws. We will see chi-square distribution further in the chapter. So here are general formulas in any continuous distribution. Okay, to calculate the expectation, it's calculated thanks an integral, the variance thanks a new integral, and you can develop and try to transform this writing to find out this formula that you already know on the variance. Okay, so it's just for your information, but we won't use these formulas like that for the following of our lessons and exercises. Okay, in the normal law, we will have tools and knowledge to find, or maybe we will know at the beginning of an exercise, the expectation and the variance or the standard deviation. So it won't be a problem for us, but it could be. Maybe if you go on third year, okay, of studies. So now let's talk about the normal law itself. A general definition, which is not very funny, but it has to be here. First, the normal law is described by, or written by the letter N, of course, and works with two parameters. These two parameters are, in fact, its expected value, so the average value, the mean, and its standard deviation. So you've got the two values that I give as functions or as formulas here by something that define a normal distribution. Okay, so you have to know them if you want to perform calculations in a normal distribution. So well, we will see in exercises how to use them and how to know them. So now, if a random variable x that is a continuous one is described by a normal distribution, then it's by a probability density, the one that gives the curve, okay, whose function has an expression which is that. So it's not very simple, but if you have a closer look, you can see that this fraction is actually one fixed coefficient because sigma is meant to be known, pi is 3.14 and so on. Okay, the number pi of mathematics. So this is a given number, a parameter, a coefficient, sorry. Mu and sigma are known. The only variable in the whole expression here is only x. So you can see that it's squared, and that's a minus sign before it, okay? And it's inside an exponential function. So this kind of expressions lead to bell curves. Bell curves look like that, okay? They look like a bell, a church bell, okay? You could be fooled by the way the curve is drawn here. It tends to 0 as x tends to infinity. So positive infinity or negative infinity. Okay, it's never 0, even if it decreases very quickly, but it tends to 0 only at infinity. So an example with a mean value of 6, and you can see that 6 is indeed the central value here, so it represents the symmetry axis of the curve, and the standard deviation represents the way the curve is going to the right or to the left quickly or not. Okay, that's all. So the lower is the standard deviation, and the thinner will the curve be. Another example here, you can see exactly the same curve, but the values on the axis have changed compared to the first graph. It's because we change parameters of the normal law, but for every normal law, you got exactly the same curve. If we choose your scales on the right axis the right way, okay? So it's always the same kind of distribution. Okay, now let's go through something that will be more and more usable in exercises, okay, to know how to use, to enhance our abilities to use the normal law. So, what are some characteristics of this bell curve? First, the central position corresponds to the mean. So I took here the law n 25, 10. So the mean is 25, the standard deviation is 10. I can place on the right and on the left the value of the standard deviation, 10. So 25 plus 10 will lead to 35, and 25 minus 10 will lead to 15 here. And you can create some area under the curve that corresponds to measures that are closer than one standard deviation from the mean. Okay, so measures between 15 and 35 here. The bounds of this interval lead to points that are not whatever points in the curve, okay, that corresponds to inflection points of the curve. So if you run to the curve from the left, for example, from the left to the right, you can see that you turn to the left here. Let's imagine it's a road and you are in a plane, okay? And you just look at the road on the ground. A car is turning on the left, and from this point, the car is beginning to turn on the right. And from this second point, the car begins to turn again on the left. So you've got what we call in mathematics inflection points. So that corresponds to the interval mu minus sigma, mu plus sigma. In terms of vertical values, it corresponds to approximately 60% of the maximal 8 of the curve. Okay, so the vertex of the curve. So it's true for any normal distribution. Okay, always approximately 60%. Now we can talk about probabilities. What is the probability that in a normal distribution, some measure would be between mu minus sigma and mu plus sigma? It's always the same probability. Whatever the coefficients or the parameters of the law, it's approximately 68.3%. And you can consider that if you take not one standard deviation, but two standard deviations, you will be able to know in advance the probability to be between the two bounds of the new interval. And in fact, you could consider any coefficient in front of the standard deviation that multiply it. If you want 1.5 standard deviation, so you stop at 10 and 40, you can know in advance the probability to be between 10 and 40 in this normal distribution, and so on. We've got results that have already been calculated. And then you can consider you're lucky, because calculating a probability in a continuous distribution implies calculate an integral. And it's not very fun or easy to calculate an integral, especially in a normal distribution that is clearly impossible if you want to perform an exact or a correct calculation. So values have been already calculated approximately, but with a good accuracy, and are given in a table, but are also in the memory of your calculators, for example. So you just have to know what to ask to a calculator. The calculator will give you the answer directly without manual calculations. But we will see that in the following of the chapter, we will need to perform some manual calculations that won't be integrals, okay, thanks to you, but that will be some transformations of writings. So we will have to describe in this video from now some general abilities of calculations. Now, let's say something more, something better than this 68.3%, and let's see that what you have to know. You have to know these 4 graphs by heart, okay? You have to know in your head that if you go to one standard deviation on the left and on the right, you are creating an interval that contains 68.3% of the possibilities. So this percentage of the total area under the curve. If you take 2 standard deviations, you are considering 95.4% of the possibilities. If you consider just a little bit less than 2, but 1.96 standard deviations on the left and on the right from the mean, you are considering 95% of the possibilities. And if you want 99% of the possibilities as a centered interval, you have to consider 2.58 standard deviations of variations in addition or in subtraction for the mean. From the mean, sorry. So this result tell you that whatever the parameters of your law, they are always the same. And that's why even in high school, okay, you already encountered this kind of value, 1.96, 2.58. That the way in the normal law to target a probability of 95% or of 99%. Okay, but with a centered interval, centered on the mean, of course. Okay, so it's been used for fluctuation intervals and for confidence intervals in high school, and it will be again here in our chapter. Now, we noticed that, or I made you notice that, whatever the parameters of a normal law, the shape of the curve was always the same. You can draw always the same curve and only change the values on the first axis and on the second axis, and then it will be the graph of the normal law that you are working with. So maybe it could exist a standard normal law that could appear as a reference of all normal laws and that could talk about all of them in one. This normal law that has been chosen with parameters 0 and 1. So it's the normal law whose mean is 0 and whose standard deviation is 1. The curve is this one. The maximum y value, ordinate is 0.4. Okay, it's not very important for us. In fact, the central value, this is very important, is 0. This is the mean of the law. And you've got a scale given by the standard deviation 1 that corresponds to inflection points of the curve. Okay, just a little comment. And you can see that if you go to 2 standard deviations on the left and on the right, you've got a large portion of the global area that is covered. 2 standard deviations, yes, it corresponds to 95.4% of the total area. Okay, so in this normal distribution, the formulas of the previous slide are simplified like that. Okay, that's just the same formulas as earlier, but mu equals 0 and sigma equals 1. And you have to know that by heart as well. So now let's have some formulas that come from the fact that a probability is an area. And it doesn't be especially linked with the standard normal law. So let's see some graphs and some formulas. You know that you are able to calculate probability to be less than a number if you color the area that is on the left of the number. But if you want to obtain the probability to be between two numbers, you can cut your calculation into two more simple calculations. And why is it this way? Why the probability of u being between a and b is the probability of u being less than b minus the probability of u being less than a? Because this graph, if you consider two values a and b on your axis, the probability to be less than b is this colored area. And if you subtract this one, the rest is exactly the area between a and b. So what you want here. So you can trust and apply this formula as long as it appears in an exercise and as long as you need it, of course. A second formula is that the probability to be more than a is 1 minus the probability to be less than a. So I put here in my formula a more than and a less than. I could have put a more than or equal to and a less than or equal to. It wouldn't have changed anything because the probability to be equal a is 0. Okay, so it doesn't have to be taken into account in a continuous random variable. So of course, the sum of both probabilities equals 1. So one of the probabilities equals 1 minus the second one. A third formula is this one, and it's not obvious, actually. So if you place a value a and its opposite value, so negative a, you can see with the symmetry of the curve that indeed the probability to be less than negative a is the same as the probability to be more than a. But it's only possible if the center is 0. Okay, if not, this formula is wrong. So the two first formulas work with any normal law, with any parameters. But the third one is only available for the standard normal law or every normal law whose center is 0. Okay, whatever the standard deviation. So you've got tools in order to perform manual calculations. And you will see later in the chapter that it's very important for us. Even if we will see also on the other hand that the use of the calculator is something that can make us directly know a probability. But we are not always interested in calculating a probability in an exercise on probability distributions. So there are other things to be done. So now, you've got a form to find out a probability. These formulas earlier are good, but they don't tell us how to calculate a probability. Okay? They just put in relation probabilities. So the form is a paper sheet, a big table full of probabilities given to you. And it corresponds to values for the standard normal law. So don't make mistake about that, okay? This form containing values of probabilities is given for n, 0, 1 only. The value that can be interesting here on the axis is given twice at the first column, or in the first column, and in the first row of the table. And the interior, so inside the table, contains probabilities. What kind of probabilities? The graph shows you that the distribution function probabilities, so the probability to be less than the value of u that you can consider. For instance, if the value of u is 0, you can see that the probability is 50%. Yes, if you place u at 0, the probability to be less than 0 is 50% because of the symmetry of the curve around 0, of course. So now how to read things like that? Now you can see that only positive values of u are mentioned in this table. We could have mentioned negative values of u because the graph consists of negative and positive values of u, but there are only positive values of u in the table below. Why? Because if you know a probability on a positive value, you can reverse the graph, okay, in your head, of course, thanks to your brain, and reverse the value of the probability. If you know a probability here, you know a probability on the left. So it wasn't necessary to put the same table with negative values of u, of course. So now, if I want the probability to be less than 1.26, I have the value of u here, approximately here on the graph, I can reach here an accuracy of 1 decimal in the first column. So it's not enough for our number. So let's see the value 1.2 at first. And the second decimal that can make you increase as accuracy will be read here, read here, sorry, in the first row of the table. So the second decimal appears at this place. Now, if you cross your readings, 1.26, you can see it corresponds to this probability. Okay, so the probability to be less than 1.26 is 8962. So approximately 89%. So you can read that, and whatever the value of u, if it gets 2 decimals and not more, of course. Okay, so you can calculate some interpolation if you want one additional decimal. If it were 1.265, you could use the result of 1.26 and 1.27 and then calculate the average of both probabilities. And it would be a good approximation of reality. So it's possible to do that, but most of the time you won't have to do that because we won't ask you so precise information. Okay. So let's say that you are able to read quickly a result thanks to this table, without asking it to your calculator, which is able to calculate this probability, of course, the same way as in this table. So, well, let's see now an additional way to calculate something manually. So we've seen earlier 3 formulas that corresponded to links between areas under the curve. Now let's see without a curve the transformation rules that work in any case, and that could make you avoid to draw a curve if you want to be sure of what to write. Well, with this law, the standard normal law, probabilities can be found without any need of graph. You've got calculation that imply P or 1 minus P, depends on the case of the calculation. And you've got some terms, some question inside P. P of what? P of U is less than something or more than something. This something could be positive or negative. So there are several different situations. Okay, in your calculation that you want to perform, you can find less than or a more than, a positive number or a negative number, and your calculation is formed with a P, a probability, or 1 minus P, because you want the complement probability. You've got 3 points. If you've got one writing, changing one of the points make you change your probability into the complement probability. Okay, if you want to have, so let's not display that. If you want the probability of P is more than 2, you can say that writing P of U is less than 2 will be the complement probability. But if you want the probability to be more than negative 2, you can say the complement to the probability of more than 2. And you could draw a graph, and my advice is do it, okay? Just push pause on this video, make a graph of the standard normal law, of course, with 0 at center, and find out that the probability to be more than negative 2 is indeed the complement of the probability of more than 2. Okay, and of course, if you're interested in the probability of more than 2, calculating 1 minus the same will be the calculation of the complement. So every time you try to change a writing on one of the 3 points, you are changing the probability into the complement probability. So now we've got a result that is an obvious one. If you use 2 transformations, you fall back to the same probability as the first one you wanted to calculate. So 2 out of the 3 possible ones, not more, not less. So you've got 2 possibilities if you want your probability. The first possibility is don't change it. The second one, okay, change the writing, but you have to change 2 points in order to fall again on the same probability. So now, why would we change a way to write the probability? Because the form in the previous slide only gives you probabilities that are less than a positive number. So what about these 3 probabilities that are not directly given by the form? So you know that the form gives you P of u is less than a positive number. So here, you would have to use P of u is less than 2 to obtain the value, but you don't want P of u is less than 2. You want, in the first example, P of u is more than 2. So you want to transform your more than into less than. But you have to use two transformations if you want to calculate the right probability. So the second transformation could be 2 into negative 2, but it's not interesting because the form doesn't take into account negative numbers. So the last transformation that is available is to transform P into 1 minus P. So if you want P of u is more than 2, you can say that it's 1 minus P of u is less than 2. You performed two transformations in writings, and if there are two transformations, you can say, or you can be sure, that this calculation will lead to the same result as this one. So, how to transform this probability into something that you can read in the form? You will transform more than in less than, and negative 2 in 2. That are your two transformations. And this probability, again, can be read directly in the form. And for this one, you won't change less than. It's okay for the form. But you have to change negative 2 into 2. And as a second transformation, P into 1 minus P. So without a graph, you can be sure that this probability is the same as this one, which is not obvious. Okay, if you consider the situation, manually speaking, okay, in terms of calculation, it's not very obvious. If you draw a graph, yes, it begins to be obvious. But here, like that, not. If you count your transformations and if you see there are two transformations, you can be sure it will be the same results. So, for your training, I'm asking you to perform exercise 16 if you have access to my document, of course. So, in the next video, we will go further and way further in calculations with the normal distribution. So, we will see the use of the calculator. We will see not only the standard normal law, but the link between it and general normal law. And we will see in the end the link between the normal law and an example among others, that is the binomial law. Okay, how could we use a normal law to talk about binomial results? And that's not obvious. Okay, so we have got another video that will contain a lot of instructions and comments and so on. So, bye for this time and see you in the next video.